All right. Okay, so we just finished our unit on forces, which was probably one of the biggest units that we're going to go over this year. But it's not that we're not going to see it again. So I want you to keep the forces unit in the back of your mind this whole time. All right, so today we are going to move on into our next unit, which is work, energy, and power. All right, so the first thing that we are going to talk about is the physics unit. I'm sorry, not the physics unit, the physics quantity of work. Now, the physics quantity of work is a lot different than, say, the definition that we give, like, I am at work right now, I am doing my job. All right, so it's not the same thing. All right, so whenever we talk about the physics quantity of work, it means that we have applied some force to move an object some distance. All right, so that gives us our first equation for this unit. All right, so work is equal to force times displacement. Easy peasy. All right, now whenever we are applying these forces, some of these forces can be applied at an angle. We saw that whenever we were in our forces unit. So if we are looking at a force that is being applied at an angle, all right, we're not worried about that force in particular. We are looking for the component of that force that is going in the same direction as the motion of the object. So remember, whenever we were given our hypotenuse and our angle, all right, we were able to use sine and cosine to find both the horizontal and the vertical components. All right, well, in this case, our direction or the component that we need is the horizontal component. All right, so we would use the cosine of theta in order to solve for that. So remember, the cosine of theta is equal to the adjacent side over the hypotenuse. Well, we're solving for the adjacent side. So that adjacent side is equal to our hypotenuse, which is our force right here, times the cosine of theta. All right, so we use that in our equation. So if we ever have a force that is being applied at an angle, we just add that cosine of theta to the end of it. All right, so we do have to take that angle into account. All right, now, whenever we were talking about forces, remember that forces were measured in newtons. All right, so even though a newton is one single letter, we found that because force is equal to mass times acceleration, we were able to derive what a newton was. All right, so we know that mass is measured in kilograms and acceleration is measured in meters per second squared. All right, so a newton is, even though it's just one single letter, it is still a derived unit. All right, so we have our base units over here that have been combined by using math. All right, so a newton is the same thing as a kilogram meter per second squared. All right, well, whenever we talk about forces are measured in joules, that capital J. All right, so just like the newton, a joule is also a derived unit. So even though it's just one single letter, it's still a derived unit. All right, so we know work is equal to force times displacement. So that tells us that 1 joule is also equal to a Newton meter. All right, so if we wanted to break that down even further, that could be a kilogram meter per second squared. Meter, which could be broken down even further into a kilogram meter squared over second squared. All right, so it can get pretty crazy. All I really want you to see is that a joule is going to be a derived unit, even though it's just one single letter. All right, now, the big thing about work is that it has to move something some distance. And there's another stipulation that we're going to talk about in just a second. But for right now, we're just going to be talking about it moving that object some distance. So say you pushed on a wall. Okay, you pushed on a wall for hours and hours and hours. You gave it everything you had. You are exhausted. You're sweating. You have exerted so much force, so much energy trying to move that wall. When in reality, that wall is never going to move. All right, so even though you put tons and tons and tons and tons of force onto that wall, because that wall never moved, you did no work. And so that's what this is saying. All right. So this is a famous statue. All right. It's Atlas holding up the earth. All right. So he is holding up the earth. That is costing him a lot of energy. He's exerting a lot of force holding it up. But because the earth is not moving, Atlas is actually doing no work. Okay, so that's something to think about. So work is only done whenever a force causes an object to move some displacement. All right, now I don't know why this picture is covering this up at the bottom, but on your notes, you should be able to see it. Okay, so I want you to put big stars right there. So work itself, we know, is measured in joules, but work is a scalar quantity. All right, so that means that whenever you calculate work by using these equations, it's going to just be that numerical value followed by joules. You are not going to put a plus or a minus in front of it. You're not going to put up, down, left, right. It does not have a direction. It is a scalar quantity. But even though it is a scalar quantity, if we look at just the forces that are at work, then we can say that those forces are doing either positive or negative work. The positive and negative is not going to come from the numerical value, all right, but we look at it by looking at the direction of the force and the direction the object is moving. All right, so I want to look at this example right here. All right, so in class, I picked up a box. All right, this would be the same thing if you pick up your backpack or if you are lifting weights. All right, so if you are lifting weights, then you are applying a force, pulling them up. All right, well, gravity is still a force that's working on them, pulling them down. And right now, it doesn't really matter if they are balanced or not. I just want you to see the two forces that are at work. Now, as you pull that box up, as that box goes up, so the direction of the motion is up. So as you move that box up, your applied force is going in the same direction as the motion of the box. So your applied force is doing positive work. Well, gravity is still doing work on it, but because gravity is going in the opposite direction as the motion, then your force of gravity is doing negative work at that time. All right, well, let's say you place that box down. All right, whenever you place that box down, you still have those same exact forces that are at work. All right, but instead of gravity being the opposite direction, gravity is now the same direction as the motion. And so at that point, gravity is now doing positive work, and your applied force is still going up, which is the opposite direction as the motion of the box. So the applied force is now doing negative work. All right. So even though work is a scalar quantity, so whenever you are calculating work, you're never going to put a plus or a minus in front of it. But even though it is not going to have a direction, if we break it down into the forces and their direction on the object, then we can tell if those or what kind of work those forces are doing. All right, now I want to skip a little bit. We're going to go to this one. Now, friction is a force. All right, so if you have something that's sliding on something else, we know that friction always opposes the motion. So friction, if your object is going to the right, friction is always going to be to the left. If your object is moving down, friction's going to be going up. If your object is moving up, friction's going to be going down. All right, if your object is moving left, friction's going to be going right. So friction, because friction is always going to be going opposite the object's motion, the only type of work that friction can do is negative work. All right, so friction can only do negative work. Okay, so friction will never, ever, ever be going in the same direction as the motion of the object. So it will always do negative work. All right, now this is the same equation as you just saw, that work is equal to force times displacement. This is just specifying the work done by friction. So if we want to find specifically the work done by friction alone, then we're just going to look at the force of friction times the displacement. All right, so we're not looking at the net force or anything like that. We're just looking at the force done by friction. All right, so go back up here. All right, so what I want you to think about, imagine this in your head. So say that you have an old-timey suitcase and you're in the airport. All right, so whenever you pick up that suitcase, all right, there's my suitcase. All right, whenever you pick that suitcase up, you have your applied force going up and you have your gravitational force pulling it back down. All right, well, whenever you pick it up, then we know, we just talked about this, your applied force is doing positive work while gravity is doing negative work. But what if you just stand there? What if you just stand there and you're just holding your suitcase, not moving anywhere? All right, well, because you are not moving, then you are doing no work. All right, so if the object is not moving, then no work is being done. But what if you started moving horizontally, like your motion was horizontal? All right, so that green line, that's your motion, that's your displacement. Now, whenever you have forces and displacement that are perpendicular to each other, those forces are not doing any work. So if your force and your displacement are perpendicular to each other, then no work is being done by those forces. Now, say if you were pushing this suitcase, all right, so if you had an applied force going in that direction, then yes, that applied force would be doing work. Friction would even be doing work. All right, it'd be doing negative work, but it would be doing work on that object. But that's because they are on the same plane. They're going in the same direction as the motion. But because this applied force and gravitational force are vertical and your motion is horizontal, all right, that means that they are perpendicular to each other, and that means that no work is being done by those forces. All right, so we have to remember that. All right, now that's all the concepts. Let's go to some examples. Let's go for some math. All right, so I want to know how much work is done on a vacuum cleaner pulled 3 meters by a force of 50 newtons at an angle of 30 degrees above the horizontal. All right, so I'm looking for how much work is done. So that is my unknown. I'm looking for the amount of work. right, so I'm given, my first given is 3 meters, which is my distance. My second given is 50 newtons of force. And I know that that force was applied at an angle. All right, so that 30 degrees is my angle. Remember that the symbol for angle is theta. All right, so we want to know our work. We know that work is equal to force times distance, but this time our force is being applied at an angle, so we only want the component of that force that goes with that distance. So we take the cosine of that angle. If you don't understand why we take the cosine, rewind just a little bit and go back to this slide right here. All right, so we have all of those. We do not have to rearrange this equation at all. So we can just plug in and go. So we have 50 times 3 times the cosine of 30 degrees. Whenever we put that in our calculator, we do need to make sure that we are in degrees and not radians. So we plug it in and we get a work of 129.9 joules. All right, if you round that up to 130 joules, that's fine with me for this one. All right, but one thing that we need to remember is that work is scalar, so there will be no direction. All right, so it's not going to be a plus 129.9 or a plus 130. It's just going to be 130 or 129.9. Okay. All right, let's do our next example. All right, we have a student who drags his physics teacher. No, we cannot do this as a demo. All right, for 25 meters on the end of a rope that makes a 40-degree angle with the ground. The force on the rope is 650 newtons. I want to know how much work is done. All right, so once again, we write down all of our givens. Our first given is 25 meters. That's our distance. All right, we know that the angle was 40 degrees, so that's our theta. And our force was a relatively large force of 650 newtons. I want to know how much work has been done. Okay, so we know that work is equal to force times distance, and because this is at an angle, we add that cosine of theta at the end, and we plug it in. So we have 650 times 25 times the cosine of 40 degrees. Now, even though these are plug and chug problems, it is still very important to pay attention to the numbers. All right, so the biggest problem that students have, even though this is super easy, is because they do not put the correct numbers with the correct variables. So please make sure that you are paying attention to where you are putting these numbers. All right, so we plug these in and we do get a work of 12,448.2 joules. Okay? All right, so that's a lot of work that they had to put in to pull me across the ground. All right, now look at this one. All right, so we have an object slides at a constant speed on a frictionless surface. First thing that I want to know is what forces are acting on the object. So this is taking us back to forces. All right, so the first thing that I want to do is I want to draw a free body diagram. All right, now we don't know what kind of object this is, but it does not matter. We know that gravity is always going to be pulling all objects down towards Earth's surface. And we said that it is on a frictionless surface. So we know that it's on a surface and all surfaces exert a normal force. Now, because this object is on a surface, we know that it is not going up and down. So we know our normal force and our gravitational force are balanced with each other. So we know it's sliding, but is it being pushed or pulled by anything? Like, do we have an applied force or a tension force going over here? No, we do not. All right, so there is no force, rightward force. And then we said that it was on a frictionless surface. So is there any frictional force working against it? Nope, no, there is not. All right, so these are our only two forces acting on the object. It's just our normal force and our gravitational force. All right, so that's our first thing that I asked you. The second thing that I asked you is, what is the work done by each force on the object? Okay, so I want to find the numerical value for the work done by each of these forces. All right, so I know that this object is traveling, it's sliding across a surface. All right, so its motion is horizontal, which means its displacement is horizontal. Well, we know that our forces are vertical and our displacement is horizontal. We know if that is the case, then these forces are doing no work on this object. Okay, so again, if we did have an applied force or a frictional force that was horizontal, those would be doing work. All right, but those are not present. So because the only two forces that we have are vertical and our motion is horizontal, there is no work being done. Okay. All right, so that is work. Hopefully you understand that. All right, we're going to work our way into energy now. See what I did there? All right, so energy, there are tons and tons and tons and tons and tons of types of energy. We're really only going to be focusing on 3 specific types of energy. All right, but energy is just the ability of a system to produce a change in itself or the world around it. All right, all that means is that energy is the ability of a system to do work. Okay, so energy is the ability to do work. Okay, so we see energy and work together. Now, we know we're going to talk about it, but I'm sure you have heard it before, you've seen it before. All right, it's something called the law of conservation of energy, meaning energy cannot be created nor can it be destroyed. All right, so you're going to have this constant changing of energy. All right, well, a change in energy, any type of change in energy, is caused by some form of work. Okay, work going in, work coming out, all right, anything like that. All right, so work causes a change in energy. So you see work and energy going hand in hand. All right, so because work is measured in joules, energy will also be measured in joules. And both of them are going to be scalar quantities. Both are scalar quantities. Okay, so like I said, we're going to be focusing on mainly 3 types of energy, but the first one is the only one that we're going to be talking about today, and that is kinetic energy. You have seen kinetic energy since you were in elementary school. Okay, so kinetic energy is normally called the energy of motion. So if you have an object that is moving, it has some amount of kinetic energy. All right, so we have used this equation time and time and time again. All right, so we find kinetic energy by using 1/2 mv squared. All right, so we know that the 2 variables that affect an object's kinetic energy are the object's mass and its velocity. And if we look at that equation itself, we can tell that because velocity is being squared while mass is being halved, we can tell that velocity is what kinetic energy depends more on. All right, we're squaring velocity and then we're halving mass. Okay, so it's the velocity that does depend, or the kinetic energy depends more on velocity than it does mass. All right, it still does depend on the mass, but it depends more on the velocity. All right, so we can use this equation to find and compare different objects, different kinetic energies. Now, if one object, so say an object, a car, all right, changes its velocity, meaning it's speeding up or it's slowing down, we know that because it's changing that velocity, it has a change in kinetic energy. Well, what did we say causes changes in energy? Up here work. All right, so work causes a change in any kind of energy. So if I have a change in velocity, which means I have a change in kinetic energy, I know that that has been caused by work. So that leads us to our last equation for today, and that is the work kinetic energy theorem. All right, so we know that our net work done on a system is going to equal that change in kinetic energy. This is the only part of this equation that you will be given on a test or a quiz. All right, so we have to remember that delta anything can be broken down into final minus initial. So what that means is that delta KE, our change in kinetic energy, can be broken down into our final kinetic energy minus our initial kinetic energy. Well, whenever we're changing this kinetic energy, most of the time it's not going to be because the mass of the object changes. All right, the mass of that car is not going to change. It's going to be because the velocity has changed. So whenever we take that into account, we know that kinetic energy is 1/2 mv squared. So we know that it's not our mass that's changing. So we keep the 1/2 m. We know it's going to be our final velocity squared minus our 1/2 m. Again, mass doesn't change, times our initial velocity squared. All right, so you have to know how to get to this part from this, because this will be the only thing that you're given. All right, so the thing that we need to remember is that whenever we have one object, a single object, who changes its velocity, so one object with a change in velocity, then we are going to use the work kinetic energy theorem. Okay, so we have a couple of examples left to do, not too bad. So let's work on this one. So we have a 7-kilogram bowling ball moves at 3 meters per second. Okay, so we're looking at a bowling ball. We have its mass and its velocity. Hopefully you're thinking of things that you can solve for with these two things. All right, but we keep going. It says, how fast must a 2.45 gram table tennis ball, so a ping pong ball, move in order to have the same kinetic energy as the bowling ball? All right, so here we are looking at two different objects. We have two separate objects. So we are not going to use the work kinetic energy theorem. All right, so what we are looking at is we have a bowling ball and a ping pong ball. All right, so we want the ping pong ball to have the same kinetic energy as the bowling ball. So we know that the kinetic energy of the bowling ball is going to be equal to the kinetic energy of the ping pong ball. All right, well, in order for us to figure out how fast it's got to be going, we need to figure out what that kinetic energy is going to be. All right, luckily, we have the mass of the bowling ball and the velocity of the bowling ball here. All right, so we can figure out the kinetic energy of the bowling ball very easily. So we use 1/2 of the bowling ball's mass times its velocity squared. So that's going to be 1/2 of 7 times 3 squared. Now remember, whenever we're doing these, we always have to remember the order of operations. All right, so the first thing that we're going to type in our calculator is we are going to square that velocity. For this one, it's super easy. 3 squared is going to be 9, but there are going to be some on quizzes, tests, homework, other problems that are not going to be quite as simple. So that's always what we put in first. All right, so we're squaring 3, so that's 9 times 7 times 1/2. That is going to give us a kinetic energy of 31.5 joules. So we know this bowling ball with that mass and that velocity has a kinetic energy of 31.5 joules. Great, I love that. All right, well, that means that this ping pong ball, we want to know how fast this ping pong ball must be going in order for it to have the same kinetic energy as the bowling ball. All right, so we know the ping pong ball's kinetic energy is also 31.5. All right, so we also know the mass of the table tennis ball, of the ping pong ball, but I want you to look. Hang on, let me write this. I can't talk and write at the same time. Most of the time. All right, so we do know the mass of the ping pong ball. We were given it as 2.45 grams. Now, hopefully a big red flag is going up in your head right now. Ding, 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 ding. That mass cannot be found in grams. It is found in kilograms. So we have to convert grams into kilograms. We know that for every 1 kilogram, there are 1,000 grams. So we divide 2.45 by 1,000, and that gives us 0.00245 kilograms for our mass. Now, I asked you, how fast must that ping pong ball be moving in order for it to have the same speed or the same kinetic energy as the bowling ball? So we are looking for the ping pong ball's velocity. All right, so we know that kinetic energy is 1/2 mv squared. We are looking for that ping pong ball's velocity. All right, now we have done things similar. We've seen this equation similar to this. Now, we could easily divide both sides by 1/2 m to get rid of those. However, whenever I have multiple things in the denominator, I have to remember to put parentheses around those. And some of you don't like to remember that. All right, so if we don't want to remember it like that, we can take it in 2 different steps. All right, so we can get rid of that 1/2 first by multiplying by its reciprocal. So I'm going to multiply both sides by 2. So that gives me 2 times the kinetic energy is equal to mv squared. Still solving for v. I can get rid of mass now by dividing both sides by it. So that's going to give us 2 times the kinetic energy divided by our mass is equal to our velocity squared. Now, our velocity is by itself, but it's not technically by itself because it's still being squared. So to get rid of that square, we take the square root of both sides. So our velocity is going to be the square root of 2 times our kinetic energy divided by our mass. So we have both of those, so we can just plug it in. So we have 2 times 31.5 divided by 0.00245. Now, that is going to give us a velocity of 160.4 meters per second. So think about how fast that is. That is super, super, super fast. All right, so that's almost as fast as the speed of sound. Okay, so the speed of sound is about 220. We'll talk about that later. You don't have to worry about that. But think about how fast that is for a ping pong ball. And while a ping pong ball can go this fast to have that same kinetic energy theoretically, that is not very probable for that ping pong ball to do. All right, so we know what it would have to be going in order to have the same kinetic energy, but in real life, it's probably not going to get to that velocity. All right, so whenever we said it depends more on the velocity than it does on the mass, here, whenever you have such a vast mass difference between the bowling ball and the ping pong ball, all right, that does play a big part in it. All right, so we're going to move on to this next one. All right, so we have a 145 gram baseball is thrown at 25 meters per second. I want to know, what is the net work done on the ball to make it reach this speed if it started from rest? All right, so here we are looking at one single object, this baseball, and this baseball has changed its velocity. All right, so what we are looking at is our work kinetic energy theorem. All right, so we have the mass of the baseball is 145 grams. Now, that big red flag should be going up. Ding, 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 ding. All right, mass cannot be found in grams. It has to be found in kilograms. All right, so we divide it by 1,000, and we do get a mass of 0.145 kilograms. All right, we have to remember that. All All right, now we know it was thrown at 25 meters per second, so that's our velocity, and I want to find the work done on it. So our work is our unknown, but we're missing something else. We were told that it started from rest. So that means that our initial velocity is 0, which means that 25 meters per second is going to be our final velocity. All right, so we know that we're looking for the work done on the ball. So we know that that is going to be the change in kinetic energy. Well, we know delta anything can be broken down into final minus initial. And we know that we can break these down, final meaning the final velocities. So we have 1/2 mv final squared minus 1/2 mv initial squared. Now, if you look at this, we love this. All right, because our initial velocity is 0. So if our initial velocity is 0, what is 0 squared? Hopefully you're saying 0. All right, what is anything times 0? That's going to be 0. So this whole thing is going to be 0. All right, so what we're really just finding is our final kinetic energy. All right, so that's going to be 1/2 of our mass, which is 0.145, times our final velocity, which is 25 squared. So the net work done on this ball to make it speed up from 0 to 25 is going to be 45.3 joules. 45.3 joules. All right, so that's all I asked you to find. All right, so what if I told you that this ball traveled a distance of 5 meters? Okay, and I wanted to know how much force was exerted to make it start moving or to make it speed up. All right, so hopefully you would realize that you have work and displacement and you're looking for force. So we know that work is equal to force times displacement. If we're looking for force, we divide both sides by our distance. So our force is our work that we just found of 45.3 joules. Our distance is 5. We divide those. This is a figurative, so it's going to be some kind of plus something newtons. All right, so we have to remember that force is a vector quantity, so it has to have that direction in it. All right, unlike work and energy. So please make sure that you remember that force does have to have a direction. All right, so that's just an example of what you're going to see on your practice. So we do need to know that we can input force times displacement in for work. All right, now this is going to be the last thing that we do today, but I do want you to put big stars around this. I want you to make sure that you can come back to this really quickly. This looks like a fantastic quiz or test question because it is bringing so much into it. All right, so the first thing that I want you to find is to determine the amount of work that must be done by the engine of a 500 kilogram race car to change the velocity of the car from 55 meters per second to 60 meters per second. All right, we know that we have one single object, that race car, and that race car is changing its velocity. Well, we know if we have a change in velocity, that tells us that we have a change in kinetic energy, and any change in energy is caused by some form of work. All right, so we are going to use our work kinetic energy theorem. All right, so we know that the net work done is equal to our change in kinetic energy. Delta anything can be broken down into final minus initial. So we have 1/2 mv final squared minus 1/2 mv initial squared. Unfortunately, we do have both a final and an initial velocity, so we can't zero out any of these. So we do just have to plug and chug. All right, so we have 1/2 times our mass of 500 times our final velocity, which is 60 squared, minus 1/2 of the same mass. Remember, our mass is not changing, times our initial velocity of 55 squared. Again, be very, very careful whenever you're plugging this into your calculator. You have to square that velocity first. All right, so whenever we square 60, that's going to give us 3,600. Multiply that by 250, that's going to give us 900,000. Minus 55 squared times 250 is going to give us 756,250. So we subtract those. So the net work done by the engine of this car to increase that velocity from 55 to 60 is a whopping 143,750 joules of work. All right, woohoo, yay. All right, now we know that if this change in velocity was accomplished in 3 seconds, all right, we can calculate the acceleration of the car. All right, now acceleration is something that we covered first semester. So we have to remember that acceleration is going to be that change in velocity over our time interval. So we know that a delta anything is going to be final minus initial. So we have our final velocity minus our initial velocity. So that's 60 minus 55 divided by our time interval of 0.3. That's going to give us 5 divided by 0.3, which does give us 16.7 meters per second squared. Now remember, acceleration is a vector quantity, but we can't just put a plus or a minus. So if we go back up to our situation, we know that we are moving east, so that's in the positive direction. And we're speeding up in the positive direction, so that tells us that the sign for our acceleration must also be positive. All right, so speeding up in the positive direction means that our acceleration is also positive. So we have a positive 16.7 meters per second squared. Now the last thing that I've asked you to calculate is the net force applied by this engine to cause this acceleration. So we should remember this from Newton's second law. We know that the net force exerted on an object is equal to the object's mass times its acceleration. We know its mass is 500 kilograms. We just found that acceleration to be 16.7 meters per second squared. We multiply those, we do get 8,350 newtons. Remember that force is a vector quantity, and our net force and acceleration will always have the same direction. So the net force applied is a plus 8,350 newtons. All right, as always, if you have any questions, you know where to find me.